We have already discussed about resource allocation graph and the types of resource allocation graph, single instance graph and multi-instance graph. Next we will discuss how to avoid deadlock using resource allocation graph. Deadlock avoidance with resource allocation graph is used for single instance resources. The banker's algorithm that we had discussed earlier can be used for both single instance resources and multi-instance resources, but this method is used for single instance resources. So for multi-instance resources, we use banker's algorithm. For single instance resources, we can use either banker's algorithm or the resource allocation graph algorithm, and this resource allocation graph algorithm can work more efficiently than the banker's algorithm. So for any deadlock avoidance approach to work, the system should have some prior information or additional knowledge such as which all processes will be executed, overall which are the resources required by the processes, and the resources which will be required by each process during the execution. So the processes usually claim in the beginning itself which all resources will be required for it during the execution. To represent that, in addition to the request edges and the assignment edge, we use one more edge in the resource allocation graph for deadlock avoidance, that is claim edge. The claim edge points from the circle representing the process to the box representing the resource, showing that the process claims that it will be using this resource during the execution. So actually during the execution, the process may use the resource or sometimes may not use the resource, but the process claims that this resource will be required by the process. This resource is expected to be required by the process during the execution. Now when execution starts, when the process comes to know that it really needs that resource, then the process will request for that resource. Then we will convert this claim edge to the request edge. And if the resource is available, we will allocate or assign this resource to the process. Then we will convert this request edge to the assignment edge. So suppose P1 and P2 are the processes which are going to be executed in our system, and they need the resources R1 and R2 for their execution. Suppose P1 claimed that it will be using R1 and R2 during its execution, and P2 also claimed that it will be using R1 and R2 during its execution. So how the deadlock avoidance method works? The system will always be kept in a safe state in the very beginning when resources are not allocated to any process. The initial state, we can consider the initial state as a safe state. A safe state is a no-deadlock state. Now, when the processes started executing, they will start making requests. Whenever some request is received, the system analyzes whether granting that request will lead to a safe state or an unsafe state. If granting the request will lead to an unsafe state, then that request will not be granted. System will remain in the current state itself. If granting the request will lead to a safe state, then that request will be granted and system will move to that new safe state. So here now resources are allocated to the processor. So now our system is in a safe state, a no deadlock state. Now suppose processor started their execution and we started receiving the requests. So we received a request from process P1. P1 is requesting for the resource R1. So if this request is granted, what will be the next state of the system? If this request is granted, P1 is requesting for R1, so we can convert this claim edge to the request edge, showing that P1 is requesting for the one instance of R1. And the R1 resource is available, so we will be able to allocate or assign this resource to P1. So we can convert this request edge to the assignment edge, showing that R1 can be allocated to P1. So if this request is granted, this will be the next state of the system. Now how to check whether this next state is a safe state or an unsafe state? Check for any cycle in this graph. If there is some cycle present in this graph, it means this is an unsafe state. Here there is no cycle in the graph, it means this is a safe state. So this request will be actually granted and system will move to that state. Now this is the current state of the system and processes are being executed. So we are receiving another request from P2. P2 is requesting for R1. If this request is granted, what will be the next state of the system? P2 is requesting for R1, so this claim edge can be converted to the request edge first, showing that P2 is requesting for R1. But the resource R1 is not available, so we cannot grant this resource now. So the request edge will remain, so it cannot be converted to the assignment edge. So if this request is granted, this will be the next state of the system. Now check whether this next state is a safe state or an unsafe state. Here also there is no cycle, means it is a safe state. So this request will be granted and system will move to that safe state. Now this is the current state of the system. Now we are receiving a new request from P2. P2 is requesting for R2. If this request is granted, what will be the next state of the system? P2 is requesting for R2. So convert this claim edge to the request edge first. And the resource R2 is available. So we will be able to assign this resource to the process. So we can convert the request edge to the assignment edge or allocation edge. Now check what is the state of the system, whether it is safe or unsafe. Check whether any cycle existing in the graph. Here there is a cycle in the graph. It shows that this state is an unsafe state. So if this request is granted, then we will be moving to an unsafe state. So this request will not be granted and the system will remain in the previous safe state or in the current safe state itself. Now whether this unsafe state is a deadlock state? No. Here the process has claimed that it will be using R2 during its execution. It may or may not use this resource R2 during the execution. So the unsafe state itself is not a deadlock state, but it may lead to deadlock in the future. And also there is chance that it may not lead to deadlock. For example, suppose during execution P1 finds that it doesn't need the resource R2, it just needs the resource R1 for its execution. So P1 is complete the execution with the resource R1. Now both the resources R1 will be free, hence R1 can be allocated to P2, then P2 can also be completed. So we will be able to execute both the processes without causing any deadlock. But if we allocate R2 to P2 and we move to that unsafe state, and after that unsafe state, if P1 requests for R2, then we will be converting this claim edge to the request edge. Now we can see an actual deadlock state here. Here the processes are all deadlocked. Here there is a cycle with the request edges and the assignment edges, and P1 is holding one resource waiting for another resource. P2 is holding one resource and waiting for another resource. Both the processes are blocked, causing deadlock. So from this unsafe state, there is chance for deadlock and not deadlock, but the system cannot control the move from the unsafe state to the deadlock state. But system can control the move from the safe state to the unsafe state. So what we do, we control the move from the safe state to the unsafe state. We will not move to this unsafe state. For that, this request will not be granted. System will remain in the safe state itself. So P2's request is not granted. So after some time, if P1 is requesting for R2, then R2 will be allocated to P1. P1 will complete its execution with R1 and R2. When P1 completes the execution, R1 and R2 will be free. Both can be allocated to P2 and P2 can complete the execution. Thus both the processes can be executed completely without causing any deadlock. This is how we avoid deadlock using resource allocation graphs.